Hi everyone, Bill Stubbs here with the 7th video in my series, Dissecting the Standard Model of Particle Physics. This one entitled, All in the Family. In this video, I continue discussing the contents of my book, Three Quarks Missed the Mark, by developing models of the muon, the pion, and the kaon consistent with the electron model developed in video 6, showing that, based on its ancestry, the muon likely inherited its general structure from the pion, and revealing that, given their models, these three particles, the electron, the muon, and the pion, and some of the kaons, are all about the same size. Let's begin. Video 6 showed that configuring the free electron as a beta electron orbiting an electron neutrino provides a physical mechanism that corrects the Bohr magneton approximation of the electron magnetic moment to its actual value. That value is 1 plus the electron anomalous magnetic moment, A sub e, of 0.0011596 times the Bohr magneton, or 1.0011596 mu sub b. This raises the question, since the actual muon magnetic moment is 1 plus its anomalous magnetic moment times its equivalent to the Bohr magneton, can a similar model treatment be determined for the muon? The muon equivalent of the Bohr magneton, call it the muon magneton, mu sub m, is its charge, q sub mu, times h bar over 2 times its mass, m sub mu, or q sub mu h bar over 2 m sub mu. Since the charge of the muon and that of the electron are equal, q sub mu equals q sub e, the only difference in the magnetons of the two is their masses. The electron mass, m sub e, in the denominator of the Bohr magneton expression is replaced by the mass of the muon, m sub mu, to make the muon magneton. This makes the muon magneton, mu sub m, equal to the Bohr magneton, mu sub b, times the ratio of the electron mass to the muon mass, m sub e over m sub mu, which is approximately 1 over 207. The actual value of the muon magnetic moment is 1.0011659 times mu sub m, so its anomalous magnetic moment is A sub mu equals 0.0011659, close to the electron anomalous magnetic moment, A sub e equals 0.0011596. If there are 207 beta electrons and positrons making up the muon, then the moment of charge produced by them generates the additional muon magnetic moment over its magneton. This suggests that, like the beta particle in the electron orbiting its neutrino to form it, the 207 beta particles in the muon orbit a muon neutrino to form the muon. Recall that the moment of charge of the beta electron in the free electron is I sub e equals 2/5 q sub beta r sub beta squared plus 2/3 q sub beta r sub e squared. This is 1 plus 3/5 r sub beta squared over r sub e squared times 2/3 q sub beta r sub e squared, which makes the electron magnetic moment 1 plus 3/5 r sub beta squared over r sub e squared times 2/3 q sub beta r sub e squared f sub e, or 1 plus 3/5 r sub beta squared over r sub e squared times mu sub b, the Bohr magneton, where f sub e is the electron frequency. Since the muon has the same net charge as the electron, the muon moment of charge is I sub mu equals 2/5 q sub beta r sub beta squared plus 2/3 q sub beta r sub mu squared, or 1 plus 3/5 r sub beta squared over r sub mu squared times 2/3 q sub beta r sub mu squared. When this I sub mu is multiplied by the muon rotational frequency f sub mu, it gives the muon magnetic moment of mu sub mu equals 1 plus 3/5 r sub beta squared over r sub mu squared times 2/3 q sub beta r sub mu squared f sub mu, or 1 plus 3/5 r sub beta squared over r sub mu squared times mu sub m, where mu sub m equals 2/3 q sub beta r sub mu squared f sub mu. The difference between the Bohr magneton and the muon magneton is the masses of the electron and the muon. Since there are no mass terms in the moment of charge, this difference apparently manifests itself in the frequencies of the particles. The electron frequency is 207 times the muon frequency. Therefore, since 2/3 q sub beta r sub mu squared f sub mu is the muon magneton, the muon anomalous magnetic moment A sub mu becomes A sub mu equals 0.0011659, which equals 3/5 r sub beta squared over r sub mu squared, or r sub mu equals 22.69 r sub beta. The muon radius is essentially the same as the electron radius of 22.75 r sub beta. The muon is just a heavier, denser version of the electron. It appears that, to produce its magnetic moment, all 207 of the muon's beta electrons and positrons must be orbiting the central muon neutrino at a radius r sub mu, and their orbits must precess about an axis through the neutrino. The simplest way to model this is to put each beta particle in an individual orbit around the neutrino. That would make the muon 207 orbits of beta electrons and positrons. However, since each orbit passes through the equator of the muon twice, and the width of a beta particle is 2r sub beta, each beta particle contributes 4r sub beta to the muon circumference. Therefore, the 207 beta particle orbits would make the muon circumference 828 r sub beta. Since the muon circumference is 2 pi r sub mu, this makes the muon radius r sub mu equal to 828 r sub beta divided by 2 pi, which is 129.87 r sub beta. This is more than 5 times the muon radius of 22.69 r sub beta from the magnetic moment calculation. This is not right. This problem can be resolved, however, by putting 6 beta particles, 3 positive and 3 negative, in an orbit. This reduces the 207 orbits with 1 particle in them to 34 orbits with 6 particles and 1 orbit with 3 particles for a total of 35 orbits. With 35 orbits, the muon circumference is just 35 times 4r sub beta, or 140 r sub beta. If we divide 140 r sub beta by 2 pi, we get a muon radius of 22.28 r sub beta, which agrees well with the 22.69 r sub beta from the magnetic moment calculation. The resulting muon might look something like this. The alternating black and white dots are the beta positrons and electrons. The particle in the center is the muon neutrino. Only half of the beta particles are shown because the other half are on the hidden side of the model. This muon model shows why many times the muon and the electron are interchangeable. The free muon is really just a free electron with some extra mass contained within it. Even though there are 206 additional charged particles in the muon over the electron, they all cancel each other, so that they add no charge to the base electron. They only add mass, which serves to slow down the angular rotation and to make it unstable. If this model is correct, then it reveals 3 things about this class of subatomic particle. 1, there are 35 orbitals at the subatomic level available to receive beta electrons and beta positrons. 2, each orbital can hold up to 3 beta electrons and 3 beta positrons. And 3, the radius of these orbitals is between 22 and 23 times the radius of a beta electron or beta positron. Since when muons decay into electrons, they appear to pass on these traits. Perhaps they were passed on to the muons by their parents, the pions and the kaons. In video 5, we saw that pions, which appear to be made of 136 beta electron-positron pairs and a valence beta electron or positron, somehow shed 33 of their electron-positron pairs to become muons. In doing so, the remnant pions create muon neutrino-antineutrino pairs from which they take the neutrinos or antineutrinos to form the muon. It appears the resulting muons have a spherical beta shell template containing 35 orbitals that each hold up to 6 beta electrons and positrons. Because the orbital radius of the betas in the muon is the same as the radius of the beta in the electron, when the muon decays, it apparently passes the template on to the electron, which has only a single beta electron or positron forming it. Consequently, even though the 35 orbitals are there in the free electron, with only one beta electron or positron to occupy them, 34 orbitals go undetected. The free electron got its beta orbital shell from the muon, so where did the muon get its 35 beta electron orbitals from? Apparently, the pion it decayed from. The pion must have contained the 35 orbitals and passed them on to the muon as a result of the decay. However, the muon orbital shell only contains 103 beta electron-positron pairs, while the pion appears to be made of 136 pairs. Where are the other 33 pairs housed? Most likely at the center of the pion, where the neutrino resides in the muon and the electron. The 33 pairs probably form a cluster at the center of the pion, around which the 207 beta electrons and positrons that form the muon orbit. Having this cluster at the center of the charged pion, enclosed in the muon shell, provides a mechanism for the charged pion to almost always decay into a muon. The decay starts with ignition of the beta electron-positron pairs at the center of the pion. When all 33 pairs have annihilated, the muon orbital shell is left. No shifting or rearranging of the beta particles is necessary to form it. Once the pion's central cluster is gone, the valence beta electron or positron in the muon shell uses the energy from the cluster annihilations to produce a muon neutrino-antineutrino pair. From the neutrino pair, one of the neutrinos assumes the role as central particle to form the muon, and the other exits the muon. If the orbital shell is passed down from the pion to the muon and on to the electron, then the radius of the muon and the electron is the same as the pion. In video 3, we estimated the radius of the pion to be about 0.33 times 10 to the minus 15 meters, based on 8 of them tightly packed within a proton with a radius of 0.85 times 10 to the minus 15 meters. This would make the radius of the muon and the electron also be about 0.33 times 10 to the minus 15 meters. Since this radius is about 22.5 times the beta electron radius, it makes the beta electron radius about 1.46 times 10 to the minus 17 meters. Like the pions, charged kaons often decay into muons and their neutrinos. But as we saw in video 5, they can also decay into a collection of pions and even a combination of pions and leptons. This led to the conclusion that there are probably two types of particles called kaons that were labeled K sub mu for kaons that decay into muons and K sub pi for those that decay into pions. While the K sub pi kaons are thought to be collections of pions, smaller versions of the baryon, the K sub mu kaons appear to be a variation or extension of the pions. Assuming that pions decay into muons because they are made of the 35 orbital muon shell, K sub mu kaons likely decay into muons because they, too, are made of the muon orbital shell. If so, one might model the K sub mu kaons as pions are modeled here, with a cluster of beta electron-positron pairs at the center of the 35 orbital muon shell, but with 380 pairs instead of 33. Assuming the radius of a beta electron or positron is the 1.46 times 10 to the minus 17 meters we calculated earlier, each beta particle has a volume of 1.3 times 10 to the minus 50 meters cubed. if there are 380 beta electron-positron pairs, or 760 betas, in the central cluster of the kaon, then they have a total volume of about 9.9 times 10 to the minus 48 meters cubed. When tightly packing large numbers of smaller spheres in a large sphere, the smaller spheres fill about 74% of the larger sphere's volume. Therefore, a spherical cluster of 380 beta electron-positron pairs fit in a sphere of volume 1.34 times 10 to the minus 47 meters cubed. A sphere of volume 1.34 times 10 to the minus 47 meters cubed has a radius of 1.47 times 10 to the minus 16 meters, or 0.147 times 10 to the minus 15 meters, which easily fits within the muon orbital shell radius of 0.33 times 10 to the minus 15 meters. Therefore, the case of mu kaon probably looks something like this: a muon shell with a cluster of 380 beta electron-positron pairs in it, essentially a pion with a larger central cluster, a heavy pion. Now, like the pion, if the beta electrons and positrons in the central cluster of the case of mu kaon completely annihilate each other, the energy created inside the muon shell along with the valence particle of the shell can create a muon neutrino-antineutrino pair. The shell can keep whichever neutrino aligns with its valence particle to form either a positive or negative muon and eject the unused neutrino. The case of mu kaon decays into a muon. Now, it appears that the K mu kaon, the pion, the muon, and the electron are all part of a family of subatomic particles made of the 35 orbital shell. We will call it the muon particle family because all three of the other particles have ties to the muon. The kaon and the pion can decay into it, and the electron decays out of it. Knowing what we do now about the models of the K mu kaon, the pion, and the muon, can we develop credible models of the K pi kaon and the tau lepton? We will attempt to do so in video 8.